So the next is Koyun Huang from Leiden Observatory. And Koyun is going to talk about the chemical footprint of AGN feedback in the outflowing circumnuclear disks of NGC1068. So please.
Thank you for the introduction. Sorry, I muted myself for a second. Yeah, good morning, everyone. First of all, I would like to thank all the organizers of this meeting, and I really appreciate the great diversity covered by this science community and also the skill set especially. So in this talk, I'm going to cover one of our recent work in characterizing the gas properties in the circumnuclear disk of a nearby AGN host galaxy, NGC1068. So with this study, we utilized multi-line molecular study thanks to ALMA, and also combined with our modeling, we were able to investigate the disk and within. So sorry, the background. This galaxy, NGC1068, it's a nearby and AGN starburst composite galaxy. So these two traits makes this an interesting target that has been intensively studied with different science scopes. So for example, with a moderate spatial resolution, half arcsecond, we were actually enabled to resolve into the circumnuclear disk, which is spanning around a few hundred parsecs. So on this map I show on the left-hand side, this is a ALMA band 7 continuum image. So at this band, mostly contribution is from the dust. So from this map, we can see several parts of the structure. We see the CND. We also see the starburst rings at the arms, like in the outskirts of this galaxy. So our focus and our main interest is in the CND, which is at the center. The CND in the past has been found to be outflowing, which is proposed to be a result of interaction between the molecular gas with the AGN ionized wing and the jet. So such interaction, the outflow also brings up a large-scale shock in this CND region, again, spanning a few hundred parsecs. So this shock region would also likely to drive a rich shock chemistry signatures at different locations of the CND. So as an example from our paper, this is plotting the ratio between SiO and HNCO. So from, I also plotted several reference positions around the CND with respect to the illustration I plot here, the schematic. So from this map, we see a clear transition from the east part to the west part, that this ratio is transiting from greater than 1 to lower than 1. So this is just an example. We also see a lot of other chemical signatures from different species. So with this, we would like to carry out a more systematic investigation into this shock chemistry. So we performed a multi-line molecular study. By that, I mean, we utilize several molecular species. And for each species, we also need multiple transitions at the same time. So this is actually a very ideal tool to trace physical and chemical processes in our case in the external galaxies, because it covers a really wide range of critical densities. Multiple species, they are sensitive to different density already. With different J transitions, we are able to cover a really robust range. Besides, for individual species, the chemical reaction needed to bring up their abundances is also dependent on the energy available to the system. So this covers a really great variety of environment that we can study in. At the same time, besides for all the pros, we also have the cons. For example, it's often the case that the same species can be found in a very diverse environment. So it brings complexity. At the same time, for individual species that we have different J transitions, the shaping of the energy distribution over different J's would also dependent on the energetics present in the field. For example, in the schematic I present here, you will have different J trend to you will have different trend in cold or hot environment. It also depends on the physical conditions at a field. So with this set of data, but with this complexity, we actually need several stages of analysis that often covers LTE analysis, also non-LTE radiative transfer analysis, and chemical modeling. So for radiative transfer modeling, we would like to disentangle, for example, the shaping complexity due to the environment. And the chemical modeling, we would like to solve the first issue. So this is the basic structure of our analysis. And for our case, we use SIO and HNCO. Both are often used as a shock tracers, and SIO has been proposed to be a very good tracer for strong shock or fast shock. So this is based on a chemical modeling in the literature. For example, in catalog 2017, they in their series of chemical modeling, they concluded that to enhance the abundance of SIO, the fast shock is really needed. So we need a fast shock to kick the silicon off from the grain surface and then release into the gas phase and form SIO in the gas phase. At the same time, fast shock would also kill a lot of things, including one of the precursor of HNCO. But HNCO has been found that can be enhanced in the slow shock regime instead. So we still need a little bit kick, but if the kick is too intense, then this will break. So at the same time, they also have a third set of chemical modeling that involves no shock, but only the gas itself is dense and warm enough so that the mental sublimation of HNCO can still be fulfilled. So this brings such a distinct chemical origin of these two species. So from their study, they use actually Plateau de Boer interferometry observations. They found a sign of differentiation, but back then the spatial resolution wasn't great and they only have a limited set of transitions available. But based on their modeling, we were successfully proposed to ALMA to have more data on that. So summary from the chemical modeling, SIO can be noticeably enhanced in strong shock scenario, while for HNCO, strong shock is not very good for this species, but weakly shock region or non-shock region, but dense enough gas would also enhance the abundance of HNCO. So so this brings to our study. With ALMA, we are able to observe 3 HNCO transitions and 5 SIO transitions. This is all the data we have. And we were observing higher resolution compared to previous study, which is at like half arc second. This is plenty or sufficient to resolving to the different locations of the CND to see in details. Right. So based on the previous chemical modeling, we already see there is possible that these two species have very distinct or very unique chemical origins. So we different from traditionally when we often throw everything together for Radix analysis. In our study, we decided to split or separate these two species simply based on the chemical modeling thoughts. So so in our analysis, we utilize non-LTE radiative transfer analysis by Radix, and also we coupled the Radix with a Bayesian inference process. At the same time, we allowed four parameters as free parameters in this analysis. We have gas density, first column. We have gas temperature, second column. We also allow the column density of individual species to be a free parameter. And finally, the beam filling factors, because we just assume we don't know a thing about how extended the source is. So this is one example from the east side of the CND. where we see, for example, HNCO and SiO tend to trace a very different part of the gas density distribution, where HNCO tend to point to higher density and SiO tend to point to really low density, even below 10 to the 3, sorry. At the same time, there seems to be a differentiation also between in terms of the gas temperature as well. So this confirms, like, for example, for SiO, the high temperature and low density seems to be a signature of the shock region again, like strongly shocked region. For HNCO, besides, it's a bit unclear. So we also took a look of all the region we can sample around the CND. So overall, mostly, again, HNCO is tracing higher gas density compared to SiO, except for R2 region, where I plotted a green square here. So in the, as I mentioned in the chemical modeling part, if we want to go without shock, we need like gas environment that is dense enough, like greater than 10 to the 4. If we go below 10 to the 4, we might need shock. Like shock is the only scenario that could enhance the HNCO abundance. So for R2 region in particular, it goes really below 10 to the 4 region. So at this point, for HNCO abundance enhancement, we can now still exclude either scenario for HNCO. But for SiO, it's probably more clear that it's pointing to strongly shocked region. So in summary, we have utilized ALMA multi-line observations of HNCO and SiO at high resolution in the CND of this nearby galaxy NGC1068. We utilized the coupled analysis with Radix modeling and Bayesian inference process to characterize the gas properties traced by these two species. And we confirm again that chemistry in the CND is really rich, and because there is a clear chemical differentiation between these two species, but they are not the only story we saw in the past actually. So this target remains a very interesting object to keep studying. And last but not least, we also again justify our approach that multi-line molecular study is actually a really powerful tool, especially in investigating the physical and chemical properties of the gas. So if you like to check this paper, please use the QR code I attach here. So feel free to take a look at it. Thank you. I'm happy to take questions.
Thank you very much for this very clear talk and presentation. Very nice. And thank you for the insights on the chemistry and excitation analysis. Maybe I have a quick question here.
Yeah.
Do you take into account, for example, excitation from cosmic rays or hot electrons into the gas, or do you put this into Radix, or does it matter at all or not?
Not into our Radix, but we are actually planning another round of chemical modeling, particularly for these two species, to include, like you said, more chemistry inside, like cosmic ray ionization and other factors into this study.
So those could affect the chemistry, of course, but
yeah.
What about the excitation of the lines?
Right. So I think that, yeah, that's a good point. We didn't include that into our consideration, actually. So I'll have to take a look at that. Thank you.
Maybe not that easy to do, but I think it's interesting to check this.
Yeah, definitely.
Do we have questions from the chat? Yes.
Yes, we do have questions. The first question is, does HNCO only strongly shock regions like outflows, or we can only trace HNCO in slow shock regions too?
Right. So, sorry. Oops. Yeah, I like sometimes like it depends on how fast shock like you refer to. Here I dissect by below 50 kilometers per second as a cut for fast versus slow. So in my definition of slow shock versus fast shock, that HNCO abundance won't be enhanced in the fast shock region or strong shock region. So this is why we did such, we have this idea of differentiation, and then we carry on to our analysis. Does that answer your question?
I think so. There is.
Can I speak up?
Yeah, please.
Yeah. I mean, when I ask from the slow shocks, I mean, the area that we have a cloud collisions or in the star forming regions that are not really evolved, not the outflow region. For instance, the shocks less than 10 kilometers per second or something like this.
Yeah, that's right. Because yeah, we will need to do further more detailed chemical modeling. Because at the same time also working on a starburst regions, which we also see HNCO actually. So that's that part of study might point to slightly different physics and chemistry at hand. So in star forming regions, the condition will be different, right? But we still see it. So right.
Yeah, thank you.
Yeah,
thank you very much. It was a great talk, by the way.
Thank you.
Do we have time for more questions?
So maybe I can take one. So if you compare the physical conditions that you get with SIO and HNCO, compared to previous studies, do you find similar physical conditions, or is it different because those molecules are tracing different gas components?
Like comparing to previous study, well, in the literature, several analyses, they often do just jam all the species and all transitions together. So first of all, it might be not really well constrained, and this is what we also saw in our first preliminary stage of this project. We also jam everything together, and we don't see a very not a good fit nor a good pointing to gas conditions either. So we think it's, again, justified we separate these two species in terms of comparison. But like in the past, so it's a bit hard to compare how, when we drag that to separate versus,
I think it's very interesting this to show that actually the different molecules are tracing different things, and maybe you're not seeing the same.
Exactly.
Very interesting, yeah. So thank you for this, yes.
Thank you.
There is one more question. Do you plan to use other molecules associated with shocks, for example, SO2, SO, and see how they compare to SIO and HNCO?
Exactly. So there are also, like you said, the sulfur-bearing species is also very interesting to look into. So that's also a part of our scope. We also, for this particular target, this galaxy, we also have methanol that is supposed to have similar scenario compared to HNCO, like weak shock region or no shock but dense enough, like this sublimations can still happen. So we would like to see how that methanol compare with HNCO in particular. But like you said, sulfur-bearing species is one of the things we would like to look into. Yeah, so thank you.
Another one, maybe water would be interesting, but difficult to observe, but maybe H2S would be an interesting molecule to target.
Yes. Yeah, indeed, yeah.
And if we have time, I have one more question.
Sure.
So in your analysis, so this might not be directly relevant, but do you consider the full multivalent input radiation? And can you disentangle, for example, the effect of the radiation coming from the jet versus the accretion and corona, how much that affects the surrounding species or surrounding geometry of the different chemicals?
That will involve a larger scale of collaboration, I think. But that's a very interesting take, because actually we are, like I said, these shock chemistry signatures are supposed to, coming from the jet or outflow interaction. So we have collaborators working on the kinematics part of this region. So we would like to, thanks for the great idea. We will we can like probably take a look into that for the future project. Thank you.
Awesome. That would be great to see.
Yeah.
Okay, so thank you again very much, Koyun, for these very nice talks and all the replies to the questions. Thank you very much.